Today, we start a new unit. So far this semester, we have been studying classical mechanics. Classical mechanics can be broken into two sub-areas. The first one is kinematics, which is a description of the motion. So a study of trying to describe the motions. And that's all we've done so far, is we've looked at those kinematic equations that allow us to describe motion. But it doesn't matter how something started moving. We're about to start in this chapter to do the other area of classical mechanics, and that's dynamics. So dynamics is a study of what causes motion, or what causes things to change motion. We're going to start with Newton's 3 laws. The first law states that an object that is in motion must stay in motion, or an object that is at rest must stay at rest unless the object is acted on by a net outside force. So we will be calculating net outside forces. So an object that's motionless or moving will continue to be that way unless it has a net outside force acting on it. And so when we say net force, we mean add up multiple forces if there are multiple forces on the object. The second law, which we are going to use so much, the second law says that the sum of the forces, and we're going to sum them like that, has to equal the mass times the acceleration. And I want to point out that this is a vector and this is a vector, the acceleration. Mass is a scalar. We don't talk about mass having direction. So anytime you have a scalar multiplied by a vector, you're going to get a vector back, and this vector will have the exact same direction as this vector. It'll have a different number part, it'll have a different unit, but the acceleration vector direction will be identical to the net force. The third law involves two objects that are interacting with each other, and they're often called action-reaction pairs. If I were to push on this wall, the wall is pushing back on me just as hard as I was pushing on it. Equal magnitude, opposite direction. So if I push this way, I'm feeling the wall push back that way. If I wound up and hit it with my fist as hard as I could, I'm gonna feel a bigger force. And that's because I'm putting a force on the wall that's much, much bigger. That's why the wall is gonna put a big force back on my knuckles. So opposite direction, that's why the negative sign, but same magnitude. So Newton's second law is a vector. Well, what we know from our last chapter is if I have a vector, I can break it into its components, and that's just what we're going to do in solving problems. We're going to have Newton's second law in component form, x component, y component, z component. A special case of Newton's second law. So here's our second law. When the acceleration is a special acceleration, and that is gravity, we get weight. So weight is mass times gravity. I'm going to talk about weight a little more. I'm going to talk about the direction of it, but this is really just a special case, special situation of Newton's second law. So anything with mass is going to have a force. All right, and last thing on our equation sheet for this unit is that if the velocity is constant, the consequence of that is delta V is 0, because it can be moving, but it's, say, moving at 5 meters per second, 5 meters per second, 5 meters per second. It's not changing. So if I take final minus initial, the change in velocity will be 0. If the change in velocity is 0, then the acceleration must be 0, because our definition of acceleration. is change in velocity over change in time. So you can have an object that is moving and a situation where there is an acceleration, or you can have an object that's moving and the acceleration be 0. So that's a finer point that you're going to need to kind of pay attention to and think about, analyze in each problem, because we could have both situations.
Now, let's look at the types of forces that we will encounter in this course.
I'm going to step through several different kinds of forces that we're going to be using in this chapter. I will note that there are a couple of forces in the second semester. When we get to electricity, there's an electric force that we're not going to cover this semester, but we'll return to these same ideas in the second semester of the course. All right, so our first one is tension. We are going to have the tension force anytime that we have a string or a rope. There will be tension. And the tension, so there's some kind of rules that go along with tension. It always acts the same all along the rope. Always acts the same. So in what I've drawn here, this is supposed to be a ceiling and a pulley with 2 boxes, A and B, with the rope that goes around them. And so the tension is always identical throughout the rope. Another thing that we'll have to make sure we remember with tension is it always points away from the object. So the tension vector for A is up, and it is also up for B. If I had drawn this differently, like this way, and we'll do some problems like this, but let's suppose I had 2 boxes that were attached with a rope. The tension in this rope acts that way for B and that way for A. So it's uniform along the entire rope, and it always acts away from the object. Next one that we're going to encounter is a spring force. And I will note that the book that we are currently using in this chapter has doesn't have this negative sign. And then when we get to this in physics 2, all of a sudden the negative sign appears. So we're just going to start out with this as it should be. This is Hooke's law, and this helps us to calculate the force from a spring, where K is the spring constant and delta X is how far the spring has been displaced from equilibrium. Because of this negative sign, the direction of F and X will always be opposite of each other. And I'm going to note when you do calculations, K is always a positive number. All right, so this shows mass on a flat surface attached to a spring, and I've labeled equilibrium, X naught. So that's it at rest. If I compress this spring this way, I have changed the location by moving to the left. My restoring force goes to the right. So, and that's what would happen if you push that up. The spring is going to want to push back that way. On the other hand, if I stretched it out, my delta X is that way now, and my restoring force is the opposite direction. So keep in mind, these spring forces, F and X, are always opposite directions. All right, let's come over here and look at our next 2 forces. I'm going to start with weight. Weight is a special case of Newton's second law. Newton's second law is F equals ma. In the special case where the acceleration is gravity, the force is weight. So anytime I have an object with mass, I will have weight. Weight always acts directly down. So I have a box on a flat surface, weight acts directly down. I have a box on a ramp, Notice weight acts directly down. So anytime you have an object with mass, there'll be weight. It doesn't have to be sitting on the surface. It can be hanging. So in the one I drew over here, I only drew tensions, but there are weights on those boxes as well. Our next force is a normal force. And the normal force always acts perpendicular to the surface when you have like an object sitting on a surface. So anytime you have an object sitting or moving on a surface, there will be a normal. The normal, if you remember from your math class, normal means perpendicular. The normal is always perpendicular to the surface. So if it's flat, the normal acts up. If it's on a ramp, the normal is going to be kind of diagonal, because in both of these cases, the vector, the normal force, is perpendicular to the surface. All right, our last one that we're going to discuss is friction or drag. And friction, this is how we calculate it. Friction, we're going to use a lowercase f for friction. We're going to take the normal from before and multiply it by a coefficient of friction. This coefficient of friction is one of those few quantities in physics that doesn't have any units. It's just going to be a number, just a coefficient. Friction always opposes motion or opposes pending motion. I'm gonna break that down for you. If I was trying to move a heavy box on a floor and just keep it simple here, and I'm gonna push it this way, so I'm applying some force to push it that way. If the box is moving that way, friction goes the opposite way. Friction always opposes motion. If I had a box sitting on a ramp and it was like kind of a rough interface between the two and it wasn't moving, which way, that phrase I used was pending motion, which way would it move if the box were to, on its own, start sliding? It's going to go down the ramp, right? So that's what we mean when we say pending motion. If it were to move, it would move down the ramp. So friction acts up the ramp. In fact, friction's what's keeping it on the ramp in the first place. So that's an introduction to the forces that we will be using in this unit. And that concludes my introduction to the concepts and to the problems. You have some conceptual questions to answer to get some practice at using this before we start problem solving.